We've seen in the previous lecture the high-level idea of how we're going to use Primal-dual algorithm. But now we're going to see all of the details, and then in the next lecture, we're going to prove that this algorithm terminates in polynomial time. So we're going to prove the correctness of this algorithm. Okay. So let's recall what we have. We're trying to find we have a graph, G. We have a weight vector, W. No assumptions on W, whether it's non-negative or not. It's just a vector. And we are it's an integral vector. And we're trying to find a minimum weight perfect matching. And so in particular, we're going to assume that there exists a perfect matching, as I mentioned in the previous lecture. And if not, then the primal is infeasible, and so there's nothing to do in this problem. So we gave the primal problem, the minimization in the previous lecture, and the dual, but I'm going to write down the dual again. The dual is a maximization problem. And it looks as follows. Max over sum of yu, subject to the sum over all subsets u. Again, whenever I mention u are the odd cardinality subsets, including the subsets of size 1, unless I specify otherwise. So it's a sum over all of these u, and I won't always write that u has odd cardinality, but it should be understood, such that an edge is contained in delta of u. In other words, there's an edge with an endpoint outside of u and an endpoint inside of the set u. This has to be less than or equal to we for every edge e. And also we have non-negativity, but again, this comes just from duality. Non-negativity is only for the constraints that are not equality constraints in the primal. And if you look back, you'll see that this is true for any u of odd cardinality, but also cardinality bigger than 3 and also odd. Okay. We are, throughout this, going to maintain a subset of the dual variables which we're allowed to use. And in this slide and the next, I'm going to explain exactly what the algorithm will maintain. So we're going to let throughout this y be a dual feasible solution, and its support set, which I'll denote by omega. Again, these are all the subsets u such that yu is strictly positive, will be laminar. So in particular, this is not something that follows automatically, but in our primal dual algorithm, when we initialize with some dual solution and when we update the dual solution, we need to make sure that we are maintaining laminarity at all times, and this laminar set will also be changing. Now, the core of the primal dual algorithm is to see which constraints are tight in the dual, and therefore what that allows me to use, what variables are allowed to be non-zero in the primal. And that is going to come from these constraints. And I will define this, and note that we have a constraint for every edge. So this essentially will say which edges the restricted primal is allowed to use. And I'll index this. If E is the full set of edges, I'm going to let E subscript y, where y is my dual feasible solution, to be all edges E for which this constraint is satisfied with equality. In other words, such that we minus sum over all u, again u odd cardinality, such that E is an element of u, yu is equal to 0. So this is the tight edges, or these are the edges that the restricted primal is allowed to use. And therefore, accordingly, I'm going to let gy be the graph that has the same vertices, v, but only has these edges. So as we've now mentioned many times, if we find a maximum, a perfect matching in gy, we are guaranteed by duality theory, namely complementary slackness guarantees this, that matching is also an optimal solution to the primal. In other words, a minimum weight matching. So this lecture is all about how we're going to do this, how we're going to either find such a maximum, a perfect matching, or update y, and therefore update the set E sub y, and then get to resolve the restricted primal. But we have a bunch of notation that we need to define in the meantime in order to get there. So if omega, as listed above, is the support of y and it's assumed to be laminar, then let me define omega max to be the inclusion-wise maximal elements of U, of omega. So let me draw the picture that we've now seen many times before. My laminar set, an example of a laminar set. Okay, so this is laminar. So in this case, omega max, which is going to be the inclusion-wise maximal elements of omega, would have 4 elements. It would have this one, 1, 2, 3, 4. So that would be omega max. And as you can see from the example, omega max is a partition of V. In other words, the union of omega max is all of V, and every element in omega max is disjoint. Unlike, of course, every element in omega, since they're allowed to be nested. So now I'm going to define G dash, and G dash is going to be the main object that we're going to be working with, and this is going to be the graph gy, in other words, the graph on all the vertices, but only with the edges that are allowed by complementary slackness, and this is why we've got a y in there. I'm omitting the y in G dash, but you should keep that in mind that G dash depends on y. So I'm contracting every single one of the maximal subsets. So in other words, in the example that I've given, let me pick a different color. G dash would have just those 4 vertices, and there would be a edge between, say, any 2 vertices. In other words, I've got U1, U2, U3, U4. These are the maximal subsets in omega max. And there's an edge between, say, in the example U1 and U3, if and only if there is an edge in gy of this. Okay, so to clarify this, G dash has an edge Ui, Uj, where Ui and Uj are elements of omega max and therefore become nodes in G dash, if and only if Gy has such an edge. So what you need to keep in mind for the rest of this lecture is what Ey is, what omega is, that's the support of our current dual solution. Omega max is the set of its maximal elements, and G dash is the new graph that's formed once I have contracted all of these nodes, all of the nodes in omega max. So what does our algorithm maintain? Again, this is just the preliminary, so we'll see exactly how this works. these two slides are meant for you to keep in mind. What are we looking to know? What is the algorithm maintaining and updating? So at each iteration, the algorithm, which we have yet to present, maintains and updates the following: omega and omega max, which we've discussed. And as always, it has to maintain it such that omega must remain laminar. Of course, it updates y and ey, and therefore gy and g dash. Ey, again, the set of allowable edges for restricted primal. Gy is that graph on those restricted edges, and g dash is that restricted graph with all of the maximal elements of omega contracted. And it also, and this is critical for expanding back, once we want to find a perfect matching in the full graph, given a matching in the restricted, in a contracted graph, we maintain a Hamiltonian cycle Cu on the subgraph that's gy of u, but where I shrink the maximal subsets of u. So an illustration of this, here is some portion of my laminar family. Maybe there's others as well. So if now my subset is that I'm concerned about, if the particular subset at hand U is this subset, note U is not itself maximal. We're maintaining this Hamiltonian cycle Cu for every such element of omega, every element of our laminar family. So this is U. What is our Hamiltonian cycle? I look inside of U, and there are many elements in there, but there are 3 maximal elements. So once I contract them, in the contracted graph, gy of U, contracting the maximal subsets of U, has now just 3 vertices, and therefore a Hamiltonian cycle would be something like that. Would just be this triangle. And in addition to this, our algorithm also maintains a matching. A matching on G dash. And we'll see that this can be expanded to be a matching in GY. And if this matching is perfect, then it means that we're done, as we explained in the previous lecture. So again, to belabor the point, in the spirit of primal-dual algorithms, we are maintaining at all times a feasible but not optimal dual solution Y, and we are maintaining a infeasible solution to the primal that's given by our matching. So a few special things that we should note is that the primal solution, the solution to the restricted primal, is actually always going to be integral the way we're doing it now, and is going to be so it's going to be a matching. And of course, as it always works, it's until it's primal feasible, the solution that we're maintaining to the restricted primal is going to have a better value than what's possible for the primal. And indeed, if we have a matching that's not yet perfect, we know that this will have an even smaller value than the minimum weight perfect matching, even lesser weight than the minimum weight perfect matching. Okay, so these are all of the things that we need to now keep in mind. y, gy, g dash, omega max, and also just know that we're maintaining the CU. And now what we should be interested in is, how does our algorithm do all of this? How does it guarantee that it can do all of this, maintaining laminarity of omega and so on? Okay, so here we go. The algorithm is as follows. We initialize in a way that's typical for primal-dual algorithms. For many combinatorial problems, either the primal or the dual, in this case we care about the dual because has an obvious choice or a simple choice for a feasible solution. And in this case, we're going to initialize with y being 0 everywhere. But again, I only want to talk about the coefficients of y that are in my laminar set. So as we discussed in the previous lecture, we are only going to talk about yu, where u is in the laminar set. Those yus could well be 0. They're allowed to be 0, but they could be positive. The elements of y, the coefficients of y that do not correspond to elements in my laminar set, we're not even going to discuss until we introduce those. So I initialize with initially omega, which by the way will also equal omega max, is the set of all the singletons. In other words, every individual vertex. So omega is every v, where v is in v. I'm going to initialize with yv identically 0, and the corresponding restricted primal solution, which is going to have just m being the empty set. So note that y is, this is certainly dual feasible. And the empty matching is infeasible. But satisfies complementary slackness because it uses no edges. Okay, so here's the high-level view of this algorithm, what we're going to do. So this is what the algorithm does. This is, again, a high-level description. We'll get into the exact details in the next slides. So it searches for a perfect matching in the graph G prime. That's the graph GY with all the maximal elements of omega contracted. What could happen? We could either find what happens when we search for it using Edmonds' algorithm? So specifically, what does it mean to search for a perfect matching? We do this we build alternating trees. And now what could happen when we build an alternating tree? If we find an augmenting path, well, we augment. If we find a blossom, we contract. And if we have no perfect matching, no augmenting path, and also no blossom to collapse, then we're going to update y to improve, in this case to increase, because the dual is a maximization problem, to increase the dual. And again, I want to make note of the fact that if we find a perfect matching, we are automatically done. So if found, it must be optimal. So this is what we're going to do at a high level. So let's see how this proceeds. So as with Edmonds Blossom algorithm, let's let X be the exposed vertices. In other words, the unmatched vertices of my graph G prime, which again is my graph GY, only the allowable edges that satisfy complementary slackness, with all of the maximal elements of omega collapsed. So let's let X be the unmatched vertices of G. In other words, those missed vertices missed by our current matching M, which is not primal. Okay, so what are the possible things that could happen as we build an augmenting, as we build an M alternating tree? Case one is that G prime has a M alternating walk that starts and ends in X. So an M alternating X to X walk of positive length. That's sort of obvious, meaning it has more than one, it has at least one edge of positive length. And notice I'm calling it a walk because I'm allowing the possibility that it starts and ends at the same vertex as we would have in a blossom. But for now, let's suppose that this is an augmenting this walk is an augmenting path. That is an augmenting path. Let's call this P. And in that case, we simply augment our algorithm and iterate. So we update M by M, our symmetric difference with EP. I'm using that to denote the edges in the path, and iterate. So I'll say we update and we iterate. So you can think about this as a step in the restricted primal algorithm. We're not updating omega, we're not updating Y. So this is easy enough. What else could happen? Case two. This is case. Is that G prime has an M alternating X to X walk that is not an augmenting path. Now, what does that mean? Now, that can only happen if we start with an edge in X. We first go with one of the allowable edges that's not in M. Otherwise, this vertex, the vertex is in X. The vertex would not be in X. And so something like this is not allowed. This would be something more like case one. But if we have something like this, this is a walk that's M alternating, out of the matching, in the matching, out of the matching, in the matching, out of the matching. That goes from X to X. So this is more what we have in mind when we have case two, and it's exactly what's illustrated in this situation. So in case two, if we have a walk that starts in X and ends in X, but is not an augmenting path, or does not contain an augmenting path, it must mean that no matter what it is, it contains a flower. So this, the walk must contain somewhere an M flower, which means that it contains an M blossom. In other words, it contains an odd length circuit. So let's let C be that blossom. Let C denote the blossom, i.e. the odd length cycle. And now let U be the nodes in the blossom. In other words, U is just V in C of V. And now we're ready to update. This is now the shrinking procedure. So our update is as follows. We update omega. Omega is our previous omega, and I add this new set, this new blossom. Again, you know, this blossom itself could have been made up of nodes that had already been shrunk, but there's no issues here. It's still going to be an odd size set with respect to the original nodes. What happens when I increase omega? First of all, you need to check that laminarity is maintained. So I'll leave this as an exercise. It's actually pretty simple because all omega all that U is it's going to be just a superset, a set containing nodes. And if some of those nodes were already in omega, then that's okay. We still maintain laminarity. We just now have a nested set. We've added a larger set. So this is called the shrinking operation, and it maintains, I'll just say clearly, it maintains laminarity of omega. So actually the way that we maintain laminarity is going to be essentially by construction, easy to see. What does this allow? This allows us now a new dual variable. Remember, we weren't even going to consider any of the YUs for U not in omega. So now we've got it. So we introduce YU and we initialize it with a value 0. But it's now a new variable that could potentially be increased. I update my infeasible primal solution, in other words, my matching, just by contracting, by removing those edges in C. And what else did I say my algorithm had to maintain? It had to maintain a Hamiltonian cycle inside of each U. And this is just going to be C. So you can see that these things are, we find these just by construction. Maintaining this is easy. And then, again, we iterate. So what is the algorithm so far? I form my M alternating trees. If there's an augmenting path, I add it, restart the algorithm. If I find a blossom, I contract it. I augment omega by adding an element to my laminar family, and I add a variable YU. I update my matching, and again I restart the algorithm. What's left? Case 3 is what? It is the setting where I can find an augmenting path, and also I have no blossom. In other words, this is only going to happen if in the setting where G prime has no M alternating X to X walk of positive length. What does that mean? That means that there was some element in X. I know that X is not empty, because otherwise, if X is empty, X is the set of exposed vertices. If X is empty, then I have a perfect matching, and as we've said, we stop. So there's certainly some element in X, and I start growing my alternating tree, and maybe it looks like this. And maybe there's more than one vertex in X that's exposed. And note that I'm always ending after I'm ending on what we previously called an even node. Why is that? Well, if I weren't ending on an even node, then I'd have an augmenting path, so I'd be in case 1. And what does not exist is there's no such edge like this. There's no, let me label these as, oops. Let me label these as odd and even. It'll be useful for us. I'll use script E now because I'm already using E for edges and EY, and we don't want to mix things up too much. And script O for odd and even edges. So note that there's no E to E edge. Otherwise, we have a walk that starts in X. This original node is in X. It's exposed and ends in X. It just doubles back on itself. So there is no E to E edge. Otherwise, we are in case 2. Okay. So this is what we've got. We've got a bunch of even edges and odd edges. And as I've labeled them, I'll just write it down. Let E equal the vertices at even distance from X, and O equal vertices at an odd distance. And again, note that we can't have something can't be in E and in O. You can just check that. Otherwise, we'd have an augmenting path, or we'd have a cycle. So in other words, this has nothing to do with how I formed, how I'm doing my search and putting in these edges for my walk. So now we are at the point of the Primal-dual algorithm where it is now time to update Y using the fact that the primal part of the algorithm that's searching for a matching has essentially terminated. It has found no augmenting path and no more blossoms to contract. So Edmonds' algorithm stops. The algorithm from a few lectures ago, and it says this is a maximum size matching in the graph that you've given me, and that's indeed correct. And that matching is not perfect. If it is perfect, again, we always stop. The algorithm terminates, and there would be no X. So if we've gotten to case 3, that means that Edmonds' algorithm has terminated, and it has failed to find a primal feasible point that satisfies complementary slackness. As always, Primal-dual now uses this point to improve the dual solution. So let's let D be a vector in R E dash. So E dash is the set of edges in EY that have survived after all the contractions. And let's define this such that du is equal to +1 if u is in this set of even nodes, and it's equal to -1 if u is in the set of odd nodes, and it's equal to 0 everywhere else. So now I update my dual variable update. Y gets updated by y plus theta times d for the largest possible theta. For theta as large as possible, but of course maintaining always dual feasibility. Maintaining dual feasibility. So let's see what that is. So first of all, M is not perfect. What does that mean? This of course means, in fact it's equivalent to the fact that X is not empty, which we know is equivalent to writing that there are more edges, nodes labeled E, then there are nodes labeled O. So what does that imply in turn? What happens to the dual optimal value? Dual optimal value, or objective value is what I really mean. That was, remember, just the sum of yu. That's my dual objective that we're trying to maximize. This has to increase. This increases for any positive theta. Again, because I have added theta times E and subtracted theta times cardinality of odd. And since there's more even than odd, then this increases. This is exactly what we expect from a primal dual algorithm. Okay, so now can it increase forever? So note that by assumption, there exists some perfect matching in the original graph. Otherwise, the primal is infeasible. So this means that the primal is feasible, and since the primal is a minimization, every primal feasible solution is an upper bound to any dual feasible solution, and therefore we know that we can't increase theta forever while maintaining feasibility. Hence, theta, and by theta I'm using the largest theta I can take, is finite, as the dual is bounded. Note, I'm using all of these facts. I'm using the fact that when theta is positive, I'm increasing the value of the dual. So the question for us now is, when does theta stop growing? In other words, how big, is a better way to phrase it, how big can we take theta? And this is answered by feasibility. So we need to check two things. So the answer here is this is decided by requirement of feasibility. And two things can happen. So some of the y's are increasing, some of the y's are decreasing. Remember now that part of our constraint, one of our constraints is that for every u that has cardinality 3 or more, and of course is odd, we're only talking about those, yu has to be non-negative. So it might stop if some yu becomes 0 for u an odd cardinality subset bigger than 3. Remember that subsets of size 1 are allowed to be negative. We don't have a non-negativity constraint on those. Now, what is u? U has to be in O. For u in O. And why is that? Well, that's simply because, just flipping back to the previous slide, I'm only decreasing the nodes in O, in the odd cardinality. I'm sorry, the nodes O that are an odd, the nodes U that are an odd distance from X. So it could be that some U becomes 0, and then we stop. So if that's the case, what do we do? Let me just note that if U is a single node, has cardinality 1, YV can be negative. You can check that. So in this event, what do? We do a process called de-shrinking. I subtract a node, a subset from omega. I subtract that, I remove that U, I delete it. This is called de-shrinking. And correspondingly, the variable y has hit 0. It's not contributing anymore to the dual, so now I remove it again from consideration. And since I've expanded, deshrinking or expanding, I've expanded a node, I have to now maintain my matching in the larger set, but this is easy to do. So M is just its previous edges, and I'm gonna just add the edges that I expanded. So it's and the perfect matching of Cu. Remember, we're maintaining that Hamiltonian cycle in the odd length blossom, minus V, where V was covered by M. Okay, so this is one way. This is one way where theta could stop. It's because of the non-negativity constraints. But it could also stop. It could also stop before it makes any new non-negativity constraints tight. It could stop because before, so this is case B, before some yu becomes 0, it could be that the constraint, let me make a little line here so we're not, it could be that some constraint, some constraint of the form sum of yu less than or equal to we becomes tight for some edge that for which it wasn't already previously tight. For some edge E, that of course has to be in this original edge set minus what we had before, the tight edges. Okay, so this is something else that could happen. Now let's just also note that if we do have, so you should also want to ask, wait a second, can we ever have a situation where theta can't be taken to be positive? Because looking at this example, we might ask, is it possible for some edge in EY to have this left-hand side increase? And you can see that that's not the case, that it can't happen. So if E is already tight, in other words, it's already in EY, then in fact the constraint is not changed. And why is that? It's not changed because it's already in my graph, and whether or not it's in my matching, it has, let's look back at the picture, any edge has one endpoint in E and one endpoint in O. And therefore, I'm subtracting and adding theta to the left-hand side of this constraint. So the only way that I change the value of the left-hand side of the constraint is for edges that are not in EY, that are not present. Otherwise, every edge, this balance does not change. So what have we done? We've now added a new edge, and now we're back to our restricted primal. Our restricted primal now has new edges to work with. So now RP has new edges to work with. And we iterate. So these are the things that can happen. So let me give you a picture of this deshrinking procedure, just to be clear. So we have something like, we have a situation where we have our U1, U2, U3, U4. We're stuck. We have nothing. We have no augmenting path. We don't have a walk from X to X. Now each one of these is a subset. So I'll draw in a different color what that subset was before. So oops. So it might have looked something like this. And we're going to expand one of these. We're going to expand the de-shrinking. The de-shrinking in case A is when I'm expanding one of these that corresponds to one of these nodes. So and the de-shrinking, you can see, is these are all my, this is CU1, this is CU2, CU3, CU4. And when I'm de-shrinking, then one of the nodes that I'm de-shrinking, so one of the nodes in, let's say I'm de-shrinking U1, in particular this one, in this situation, was already covered by the existing matching. So looking back here at de-shrinking, I said that I expand M, the arrows maybe are too confusing here. I expand M with a perfect matching of Cu minus V, where V was already covered by M. And we can see what happens here. So in this case, this would be that V. And if I look at Cu without that V, then indeed it would be just these four vertices, and there is a perfect matching on those. And that is always going to be the case for any odd cycle. I subtract one, I have an alternating cycle on an even number of nodes. That is going to be a perfect matching always. So this picture is illustrating two things. If I'm just de-shrinking one node, then this is how it would work. But it also shows how at any point, if I have found a perfect matching, this is an example where it is a perfect matching. I have a perfect matching on these four nodes. Then the algorithm stops and I expand to get back a perfect matching on the original graph. So this is a picture of de-shrinking, and it is also a picture of how we obtain a perfect matching in the original graph E from our perfect matching, or maybe let me call this G, in our original graph G, from our perfect matching in our restricted graph that is also contracted. So that's it. This is the algorithm. We also have to argue that it stops. So let me just summarize here what we've seen. The summary is that we try first to augment by building augmenting paths. And if we ever find a perfect matching, then we're done. We're optimal by complementary slackness. Along the way, we contract blossoms, adding sets to omega, and therefore variables to the dual, and variables to the dual. And when we're done, when we have nothing more to contract, and also when we have not found a perfect matching, we de-shrink or add new edges. In either case, we're updating y. We're increasing the value of y. This is the algorithm. In the next lecture, we're going to show that it is correct. We already can see that if it terminates, it has to terminate in a maximum matching. That is the only way that you cannot perform something in case 1, case 2, or case 3. You can always proceed with case 1, case 2, case 3 as long as X is not empty. As soon as X becomes empty, we have a perfect matching, and we've already seen in the previous lecture that that means that we have an optimal matching by complementary slackness. The next lecture will show us that the running time of this algorithm is polynomial. So we'll pick it up next time.